Welcome to Untitled Academy. This is Richard Tai. We're continuing our lessons in trigonometry. We're almost halfway through our trigonometry lessons. There's lots of lessons that we have covered so far. Today we're moving on to the next topic called solving trigonometry equations. So right now, let's go ahead and take a look at a simple trigonometry equation, and then let me go ahead and talk a little bit about what does it mean to be solving a trig equation. So a simple trig equation looks like this: 2 sine x equal to 1. Okay, that's one of the basic equation we can talk about. So what does it mean? Well, what this means is if we go ahead and divide both sides by 2, so sine x equal to 1/2. So we isolate sine x. So that's the first part of the solution. First part of the procedure is to isolate the variable term sine x. But sine x equal to 1/2, what does it mean? Well, we want to find out what angle or what value that will go into x to have the sine of x equal to 1/2 to have this equation to be true. So let's see graphically, just very quickly, to see what does it mean. So this is sine x. Okay, I already put up the graph for you guys. Alright, let's actually make it a little darker. Okay, easy to see sine x. And let's go ahead and put sine x equal to 1/2. So y equal to 1/2, which is 0.5. Alright, so now you can see there is a line. The blue line is y equal to 1/2, and the red graph is sine x. And so when sine x equal to 1/2, it basically means we're looking at their intersection points. So let's look at this. There's an intersection point somewhere here. Oh, pi over 6. And there's another intersection here, 5 pi over 6. But there's another intersection point here, 13 pi over 6. And there's another intersection here, 17 pi over 6. So as you can see, it actually has a lot of intersection points. Actually, in reality, it has infinite number of intersection points between the line 1/2 and sine x. So that means sine x equal to 1/2. I can have several answers for x. Actually, I can have infinite number of answers for x. Pi over 6, 5 pi over 6, 13 pi over 6, and so on. So how can we describe our answer sets here like this? Well, there are some problems that will allow you to limit your answer sets from between 0 and 2 pi. Okay, so when you're limited when you're solving the sine equation, and when you're limited to find only the answer between 0 and 2 pi, it's a little bit easier. You can just go through your unit circle or look at the graph and to see what was going on within 2 pi. But also, you want to go ahead and be able to write something called the general solution. So the general solution is that we have to see a pattern to see how often does the answer repeat. Now, as you remember, sine has a period of 2 pi. So everything for sine repeats itself every 2 pi for sure. Okay, so pi over 6 repeats. The next time you come back to pi over 6, actually is 13 pi over 6. Okay, because 13 pi over 6 is a coterminal angle for pi over 6. So they are the repetition here. So it repeats itself every 2 pi. But 5 pi over 6 also repeats itself every 2 pi. Okay. However, pi over 6 and 5 pi over 6, they don't. Their difference is about 4 pi over 6. Okay, so there's no actual distinction. Okay, there's not much description we can put on between those two. So what we can do is we can describe pi over 6 because that's the first answer, from 0 to 2 pi, and then how it repeats every pi. But notice it not just repeats in the when you add 1 pi, when you add 2 pi or add another 2 pi, it also repeats in the negative direction. You can also start from pi over 6 and minus 2 pi and get another answer. Okay, then you can start with 5 pi over 6. You can add 2 pi, which gets you 17 pi over 6. Then you can add another 2 pi, that will get you 29 pi over 6. Or you could subtract 2 pi from 5 pi over 6 to get negative 7 pi over 6. That's also an answer. So you see, all those are intersection points. So they are solutions to our equation. So let's come back here. So basically, we have several answers. We have pi over 6 because when x equal to pi over 6, sine of pi over 6 equal to 1/2, and 5 pi over 6. Okay, which is 30 degrees here, and which is 150 degrees there. Okay, so they equal to that. So those are specific solutions if we want to solve x between 0 and 2 pi. If x is between 0 and 2 pi, that's all you have to write. However, if you want to write something called the general solution, Alright, the general solutions would be pi over 6 plus 2m pi. Now what do I mean by 2m pi? 2m pi means it's multiple of 2 pi, and m belongs to the set of integers. Okay, so m belongs to the set of integers, and x also equal to 5 pi over 6 plus 2m pi. What does 2m pi mean again? 2m pi means multiples of 2 pi. Now, what I mean by n that belongs to the set of integers, that means n start with all the way actually from negative infinity to negative ... to negative 3, negative 3, negative 2, negative 1, 0, 1, 2, and 3, and it goes on forever. So n is any integers. Integers includes both the positive integers, negative integers, and 0. So when we say n belongs to z, the set of integers, z represents the set of integers, that means n can be any of those numbers. So when you plug in any of those numbers in there, you will be able to get the right answer. Okay, for example, if I want to get pi over 6, I plug in 0, right? That will give me pi over 6. If I want to get 13 pi over 6, I plug in 1, so that will be pi over 6 plus 2 times 1 plus pi times pi, excuse me. So that's pi over 6 plus 2 pi, which will give us 13 pi over 6. So you see, to get pi over 6, I multiply by pi over 6 plus 2 times 0 times pi. To get 13 pi over 6, I do pi over 6 plus 2 times 1 times pi. And to get 25 pi over 6, I get pi over 6 plus 2 times 2 times pi. So just want to make sure that you understand how everything repeats itself in a cycle of 2 pi. Okay, most of the time it's in a cycle of 2 pi, but sine function, cosine function does that, but tangent and cotangent repeats itself every pi. So we have to pay attention to the situation as well. Okay, all right. So let's go back here. So the general solution would be this. This would be the general solution. Okay. And you have to make sure that you identify what is n. Okay, sometimes we put 2 plus minus 2m pi, and n can be equal to 0, 1, 2, 3. That's also doable. Okay, but if we say n equal to any integers, then we can just say plus here. Okay, but this is the specific solution if x is limited between 0 and 2 pi. Okay, all right. So let's take a look at another example here. Let's take a look at the tangent function. So 3 times tangent square x minus 1 equal to 0. Alright, in the first step, just like we solve any kind of equations, we want to go ahead and isolate our expressions. So we want to move the 1 over, move the 3 over, so add 1 on both sides of the equation, and then divide by 3, so it becomes tangent square x equal to 1/3. Okay, and then we want to go ahead and take square root on both sides of the equation, so we can get tangent x. Okay, now when we take square root, you guys remember there are always how many roots? There's always 2 roots, so it's plus minus square root of 1 over square root of 3. Now that's the same as plus minus 1 over square root of 3. So now we have to look at our unit circles to take a look at when tangent x equal to plus minus 1 over square root of 3. Plus minus 1 over square root of 3. Now, let's take a look at the unit circle here. What does this mean? When tangent is equal to plus minus 1 over square root of 3, it really tells us that sine has to do with the 1 here on the top, and cosine has to do with square root of 3 on the bottom here, right? So let's go ahead and look at the unit circle and see what we can see here. Okay, let's take a look at this unit circle picture here. Now, tangent, as we said, tangent equal to sine over cosine. So looking at the unit circle, the cosine value comes first. Cosine value is x value. Sine value of the angle is y value. So like, for example, tangent of 0 is 0 over 1. Okay, so y over x, 0 over 1 is 0. Now look at this. Tangent of pi over 6, 30 degrees, which is 1/2 over square root of 3 over 2. So when you divide 1/2 divided by square root of 3 over 2, the denominators cancel out, so it becomes 1 divided by square root of 3. So that's exactly what we're looking for. Okay, because we want our angle, right? We are looking for x that makes tangent to become plus minus 1 over square root of 3. So that means, if we go back to our sign unit circle here, that means it has to be something has to do with pi over 6. So it's 1 over square root 3, okay? Go ahead and keep looking in the next quadrant here, okay? 5 pi over 6 because 1 over negative square root 3. And then keep going in the third quadrant. In the third quadrant, it will be down here, 4 pi over, oh no, I'm sorry, 7 pi over 6 because sine here is negative 1/2, cosine is negative square root 3 over 2. So you divide them, it will get you positive 1 over square root 3, and the last one is 11 pi over 6. Okay, so we think, okay, so x will be equal to pi over 6, right? 5 pi over 6 7 pi over 6 and 11 pi over 6 if x is within x and 2 pi. Okay, now how do I write the general solution here? How does it repeat? What's the pattern here? Well, it actually repeats every pi, right? 5 pi over 6 repeats itself. The next time it repeats itself, every pi is 7 pi over 6. And 5 pi over 6, if I start with 5 pi over 6, next time it repeats itself is 11 pi over 6. As you can see, they have a corresponding relationship there. So if I add from pi over 6, I add pi, which is half a circle, I get to 7 pi over 6. I add pi again, I will repeat. So in order to write the general solution, I would say, okay, it repeats every pi. So it repeats every m pi, and then I'm going to use 5 pi over 6 repeats every m pi. So that will cover 7 pi over 6, 11 pi over 6. And what does n belong to? Or what does n equal to? N belongs to the set of integers. Okay, so this would be my general solutions. Okay, general solutions. And it matches. It makes sense because we remember the period of tangent is 1 pi. The period of tangent 1 pi. So it makes sense that when we solve a tangent, you have period as m pi. Okay. All right. So let's go ahead and take a look at another equation. Now let's take a look at this example. 2 cosine square x equal to 4 cosine x minus 1. Now there are times that we have to do this using algebraic solutions, just like we solve any other equations. And this has a square, cosine square x and cosine x. So what we're going to do is we're going to treat cosine x as a unit. We're going to treat cosine x itself as a variable, as a unit. And so if you treat it like that, we can look at this as a quadratic, as an equation, trig equation in quadratic form. It's not a quadratic equation, but it's an equation in quadratic form. We can, because if we treat cosine x as one variable, we can treat this as a quadratic form. So we can solve it using our methods that are using the methods and the knowledge that we know of how to solve quadratic equations. Now before, we usually want to factor this, right? So we basically move everything. If we have a quadratic equation, for example, if we have 2x equal to 4x minus 1, something like that. If you want to solve this, 2x squared, I'm sorry, equal to 4x minus 1, you would move everything to the left hand side and set it equal to 0 and start trying to factor it or solve it. Okay, so this is our approach here. This is another way, important way to combine our knowledge of solving quadratic equation into solving trigonometry equations in quadratic form. Now, so let's see if we can factor it. Doesn't seem that like it can, because our factors are this would be 2 cosine x times cosine x. Okay, that will give me 2 cosine square x. But the factor here is 1, so this 1 and 1 only. There's nothing else we can do. And I don't see, if I go ahead and put negative and negative here, it would be negative 2 minus 1. So the outside and the inside joined together, it wouldn't give me a negative 4. It will only give me negative 3. So it doesn't seem that we can factor this. So when we cannot factor, we have to use something else. So let's go ahead and use quadratic form. Let's see, we cannot use quadratic factoring, then let's use quadratic formula. Okay, do you remember quadratic formula? Okay, let's write this as x equal to negative b, remember, plus minus square root of b squared minus 4ac divided by 2a. So this is the quadratic formula. So let's go ahead and use that. So that means we're solving for cosine x. That means cosine x is going to be equal to negative b, which is negative 4, plus minus square root of b squared is 16, minus 4 times a is 2, times c is 1, divided by 2 times 2. Okay, So let's simplify this. So cosine equal to 4 plus minus square root of 16 minus 8, which is square root 8, okay, divide by 4. Okay, let's try to simplify this a little bit further. Alright, so 4 on top plus minus 2 square root 2 divided by 4. So we can reduce everything by 2. So it will be 2 plus minus square root 2 over 2. Okay. And let's go ahead and plug in a calculator. Okay, so it will be 2 plus square root 2 divided by 2. That will come out to be about 1.7071. This is in radian. Or we can have, if you do 2 minus square root 2 divided by 2, that will be a small number. It's 0.2929 radian. Okay. Alright, so those are radian values, but how does it repeat? This is a generic, this is a solution within what? Within 0 and 2 pi. 2 pi is like 6.28, right? So how do I write the generic solutions? That means, alright, well, okay, I'm sorry. We got x, okay? This is what we got is cosine x. We haven't got x yet, okay? So, if we got cosine x equal to this and this, now pay attention. Cosine x, can cosine x be greater than or equal to 1? Well, actually, it does not, right? Because cosine x, regular cosine x, does not equal to greater than 1 or less than negative 1. So this is actually not a viable solution. This is not a viable solution. So the only solution here we got is cosine x equal to 0.2929. Alright. So how do we get back to the angle x, okay, or the value of x? Well, what we need to do is to use arc cosine. So x would be equal to arc cosine of 0.2929. Okay, so let's go ahead and take a look and see what happened. We have what will we have when we do this? We will get something about 72.96 degrees, approximately 72.969. Yep, 968 degree, 9683 degrees. Okay, but how do we go ahead and use this? Now, remember, arc cosine actually should give us one angle in first quadrant, but there's another angle that will also have a cosine value of 0.2929, which is in fourth quadrant. So how do we get that? Well, what we can do is we can take this angle. Okay, the reference angle is 72 degrees. Because it's in first quadrant, so it's reference to its angle. So in the fourth quadrant, angle will be approximately, how do I do that? I go ahead and use 360 minus this angle. So it takes 360 degrees minus this angle. That will give me about 287.0316. Okay, 17 degrees. So let me just draw a little quick diagram to show you why do I have 72 and 287. Okay. So 72 degrees, this is 72 degrees, right? So it's approximately there. So this is my angle here in first quadrant. But I remember in fourth quadrant, there's also an angle here that has the same value of cosine, because cosine is positive in first quadrant and fourth quadrant. So this angle is basically the negative 72 degree angle, or negative 72.9683 degree. So how do I get in the positive? Well, I go ahead and take 360, right? Subtract 72 degrees, then I will get 287. That's how I get 287.0317 degrees right here. Okay, so we have two angles, 72 and 287. So how do I write that using in general solutions? Well, I remember the pattern is what? For the period for cosine is 2 pi. So I can write 72.9683 degrees plus 2 pi. Well, what's 2 pi? 2 pi is 360. So it's 360 n degrees. Okay, and then it's also equal to 287.0317 degrees plus 360 n degrees, and n belongs to the set of all integers. So this is the way to represent the general equation, general solution for this equation. Okay. Alright, so let's go ahead and try another example here. Example 4. Alright, so tangent square theta plus 3 equal to 3 secant theta. Alright, so here we have two functions that are involved. Okay, now when we have two functions, it's going to be a little bit more difficult. So we have to use our knowledge of transformation, of using identities to actually combine them, to change them into one equation. So I know tangent squared theta is equal to what? Is equal to secant squared theta minus 1. So this is one way to go ahead and do it. Alright. So secant squared theta minus 1 plus 3 is equal to 3 secant theta. Okay. So let's combine everything. So secant squared theta. Let's bring everything over because I can see that there is a this is a quadratic form again. Alright. So bring the 3 secant squared theta over to becomes negative, and then negative 1 plus 3 is positive 2. Now this time let's see if we can factor this. Okay, so secant squared theta is secant theta times secant theta. Alright, we're treating secant as theta as a variable x here. So secant theta times secant theta, and 2 is just 2 times 1. Alright, so now we know that they have to add up to a negative 3, so both sides has to be negative, and negative 1 times negative plus negative 1, negative 2 plus negative 1 is negative 3. Okay, so that will work out. So now we have two factors. So we know secant theta minus 2 would be equal to 0, and secant theta minus 1 would be equal to 0. So there are two possibilities here. So we have to solve it two ways. So this, from the first equation, it tells us secant theta equal to 2 because I can add 2 on both sides. Okay, so when does secant theta equal to 2? Well, when secant theta equal to 2, when cosine equal to 1/2. So look at cosine. Cosine is the x coordinate. 1 square root 3 over 2 square root 2 over 2 1/2. Okay, right there. Pi over 3. So secant of pi over 3 is equal to 2. Then in fourth quadrant, it will again be equal to 2, so it's 5 pi over 3. Okay, so theta here will be equal to pi over 3 and 5 pi over 3. Let's go ahead and write it down first. This is between 0 and 2 pi, and then we'll write the general solution a little bit later. Secant theta equal to minus 1 equal to 0. That means secant is equal to 1. When does secant equal to 1? Well, when cosine equal to 1. When does cosine equal to 1? Right here, 0. That's the only place when cosine equal to 1. Okay, so secant equal to 0, 0 radian. Okay. Alright, then we can go ahead and write our general solutions. Now, when does everyone repeat? Well, what's the period of secant? It's also the same as period of cosine, so it's just pi. 2 pi, I'm sorry. So we can go ahead and do this. Plus 2m pi, 5 pi over 3 plus 2m pi, and 0 plus 2m pi. Okay? And then n belongs to the set of integers z. Okay, so you always want to indicate what is n, otherwise you're not making sense if you write the general solution without indicating what is n. Okay. Alright, so this is another very simple quadratic form trigonometry equations that we just solved. Okay. Now let's go ahead and try another example here. There are several techniques, several ways that we can pay attention to, but let's go ahead and look at different things that we can do, and sometimes you have to do different transformations. Alright, 2 sine phi times cosine phi equal to sine phi. Alright, so it's true that we can, it looks like people will saying, yes, let's divide both sides by sine phi. But if we divide it by sine phi, we will lose values for the angles by this operation, because then we are taking away what's part of the equation. So remember, in algebra, right, we cannot divide by both sides by x if we just want to cancel out the equation by quantity involving the unknown. So what we have to do is we want to go and move the sine phi over to the other side and see if we can go ahead do some transformation trigonometry using trig identities. Okay, let's move sine phi over to the other side. Now here we can actually factor out the sine phi. Okay, so let's factor out the sine. So it becomes 2 cosine phi minus 1 equal to 0. So now this is more approachable. This is just factoring, right? So we know there are two factors. We have sine phi times this whole factor equal to 0, so that means sine phi must be equal to 0, or 2 cosine phi minus 1 must be equal to 0. So now we can solve for two things. Sine phi equal to 0, that's easy. When does sine equal to 0? Well, if you look at your unit circle, sine equal to 0 when when phi equal to 0 and when phi equal to pi. Okay. Okay, so here phi equal to 0 and pi. Alright, what about here? Well, let's go ahead and solve it. So 2 cosine phi equal to 1, cosine phi equal to 1/2. So when does cosine equal to 1/2? I think we just did that a little bit earlier, when it's pi over 3 and 5 pi over 3 in quadrant 4, because in quadrant 2 and quadrant 3, cosine would be negative. Okay, so it's phi would be equal to pi over 3 and 5 pi over 3. Okay, so therefore we have 4 answers within within the 0 to 2 pi. But if we want to write a generic solution, general solution, we would do 0 plus 2 pi, okay, 2n pi, okay, and then pi, let me go ahead and list them in order. Pi over 3 plus 2n pi, right? And then you have pi plus 2n pi, and you have 5 pi over 3 plus 2n pi. Okay, that's the general solution. And what does n belong to? N belongs to the set of integers. Now this little e symbol, like the e symbol, is actually not z, so like little c with a dash in there, it means belongs to. So this means n belongs to the set of integers, all integers. Z represents the set of integers. This is a set notation. You have actually other variables like capital R. R represent the real number set. Okay, alright, so let's go ahead and see if we want to take a look at another example. Let's take a look at this special case. Okay, not special case, but this is a different case of equation here. Sine x plus cosine x equal to 1. Now, right now, it doesn't seem that we can do much to write change sine and cosine. Well, there's a way to write cosine as plus minus square root of 1 minus sine square x, but that will introduce a radical, so we don't want to do that. So one way to go ahead and come around with this is, let's go ahead and square both sides. The reason is, why do you want to square both sides, is because we can deal with sine square x and cosine square x much easier. So, but when we square both sides, we need to remember later on to check for extraneous solutions. That's what happens when we square both sides. We introduce some different, we introduce new solutions, but that's not true to our original equation. That's called extraneous solutions. So let's square this. Okay, so let's go ahead and square that. So it would be sine x plus 2 sine cosine plus cosine square x equal to 1. Okay. Alright, so let's see if we can go ahead and move both sides. Okay. Okay, well actually, I think I squared it the wrong way here, because when I square this, sine x plus cosine x, I introduced this expression. Now we haven't talked about what this expression equal to. Of course, this is actually sine 2x, but that will introduce us to something before our time. Okay, we haven't done the double angle formula yet, and we don't want to do that. Okay, so that's not a good idea to go. So let me go and go back. So let's go ahead and do this. Let's move cosine x to the other side, so it becomes 1 minus cosine x. There we go. Now we can square both sides, because now when we square both sides, it will be much easier. I'll have cosine on one side, sine on one side. So it becomes sine square x equal to 1 minus 2 cosine x, okay, plus cosine square x. There we go. So we don't have cosine and sine mingle together. Now sine square x is equal to 1 minus cosine square x by Pythagorean theorem, so that's going to be a good thing. Now everything is cosine, and then this becomes like a quadratic form. Let's move everything to the right hand side, or move everything to the left hand side actually. Okay. So let's move this. So we have actually, I guess we can move everything to the right hand side. Subtract 1 from both sides. Okay, so yeah, let's move everything to the right hand side here. Alright, so add 1, subtract 1, and add cosine square x. 0 equal to negative 2 cosine x plus 2 cosine square x. Okay, so I have 2 cosine square x minus 2 cosine x actually, so it's 2 cosine square x minus 2 cosine x equal to 0. Let's factor out 2 cosine x. So it becomes cosine x minus 1 equal to 0. Okay, so we can go ahead. I'm going to move it up here to this this side of the screen here. So this becomes 2 cosine x equal to 0, or cosine x minus 1 equal to 0. When does cosine x equal to 0? Well, if you go back to the unit circle here, cosine x equal to 0 when x equal to pi over 2 and negative 3 pi over 2. So x will be equal to pi over 2 and 3 pi over 2. Okay, like that. And what about this? Cosine x minus 1 equal to 0. That means cosine x equal to 1. So when does cosine x equal to 1? Well, when x equal to pi, when x equal to 0. Okay, when x equal to 0. So there are 3 angles that we need to check the solution with. So let's check our solution. Alright, so sine of pi over 2 plus cosine of pi over 2, does that equal to 1? Okay, well, sine pi over 2 is 1. Okay, cosine pi over 2 is 0, so that's equal to 1, so that check. Okay, so that means it is a solution. Good. What about sine of 3 pi over 2 plus cosine of 3 pi over 2? Alright, does that equal to 1? Sine pi over 2 equal to negative 1. Okay, sine pi over 2, 3 pi over 2 is negative 1 down there. Cosine of 3 pi over 2 is 0, so 0 plus negative 1 plus 0 is not equal to 1. Okay, so that is not a check. So that means 3 pi over 2 is not a solution. Okay, and then let's go ahead and check 0. Sine of 0 plus cosine of 0, does that equal to 1? Sine of 0 is 0, cosine of 0 is 1, so that does equal to 1. Okay, so that's check. Alright, so that means 3 pi over 2 is not a solution. Okay, it's not a solution. So our solutions, if we go ahead and want to write in general forms, it will be x will be equal to 0 plus 2m pi, and then pi over 2 plus 2m pi. Okay, and then m belongs to the set of integers. So 3 pi over 2, even though it's part of the solution, but it was an extraneous solution that was introduced because we squared both sides of the equation, and so that's why we have to check the solution to make sure it's not make sure all the solution we got is the correct one to the original equation. Okay, as you can see here, it doesn't work because when sine 3 pi over 2 is negative 1, because it's squared, so therefore 3 pi over 2 became part of the solution. Because if we square this, it will work, right? If we square this, of course it will be equal to 1 square, but because we're looking for the equation before the square, so therefore it doesn't work. Alright, so that's it for today. Thank you for joining us. If you have any questions, comments, please leave them at the comment section, and we hope to see you in next lessons. Continue to join us with our trigonometry lessons next time. Thank you.